So we're going to do first. Yeah, Ron, I'm going to go. Ron? I'm going to go. I'm going to ask you guys real quick. Okay. Welcome to the Hardcore Hackathon! Do take a seat for a few greats. We are about to kick off what I hope is a dazzling array of created apps of productivity and C++, CUDA kernels, distributed systems, everything that makes us truly feel like we are engineers. My name is Jeremy. Welcome to AGI House. Rohan, welcome. Thanks for organizing. Ash. So I actually met Ash at a hackathon, I want to say about 4 months ago, and it was this really glorious intellectual conversation. And this collaboration sort of came out of this sort of network of friendships, which is great. So this is AGI House. We've launched hundreds of glorious hackathon projects to date, and we have incredible origins. But I'm looking forward to seeing what everyone comes up with. You've been having phenomenal conversations. It's refreshing to not fully understand the nature of conversations when you're being exposed to a system that you haven't touched in a long time, maybe since college. It's been a long time since I've been implementing compilers, creating my own programming languages, that sort of thing. So it's been great to talk to you about creating DB stores, etc. The plan for the day is to ideate, come up with creative ideas. So we'll have lightning talks at the end of this session. So if you have a glorious hardcore hack that you'd love to work with people on, definitely come pitch your idea, let us know. And then we'll have 7 hours of hardcore hacking where we build what we hope are open source projects that get launched on GitHub, that trend, that have incredible impact. People have been creating variants of Stable Diffusion that execute in sub 1 second, or incredibly fast or efficient LLM completions that operate in CP. So it's a really dazzling time to basically make things that are super fast and effective. So yeah, lots of love. Let's hear it for Ash. She'll be our first speaker.
Hey guys, does this work?
It's off for now.
Okay.
Project.
So my name is Ash. I run a project called Unum, and the idea there is that most of modern software doesn't really use the hardware potential really well. The kinds of problems I generally work on are related to search in all forms, shapes, and sizes. So be it semantic or lexicographic, so embeddings or strings and that kind of stuff. And not too long ago, I moved back to the Bay Area, so I felt like some of the systems activity has been dying down during COVID in the Bay. And we thought with friends, as the guys have mentioned, Jeremy and Ron, that it's probably worth bringing everyone in together to discuss how we can build better systems, more efficient systems, more scalable ones. I implement and maintain several projects. One of them is usearch, which is a fairly fast vector search engine with bindings for 10 programming languages. Potentially might be one of the most popular ones out there. So it powers several databases, runs on mobile devices, used by different publishers for like their games and similar stuff. We also train custom embedding models, very small ones so that you can deploy them on a large scale and analyze multimodal content. But we also work a lot on low-level optimizations, mostly themed assembly. We cover x86, we cover ARM. On both of those, we cover several subsets, like 3 or 4 generations of subsets of AVX512, ARM Neon and SVE. But this goes beyond data parallel operations. So writing themed assembly for stuff like pairwise multiplication of 2 arrays is fairly simple. But doing decoding of variable length encodings or processing UTF-8, doing substring search, and this kind of stuff, it turns out that even libc, which is considered like the state of the art in many ways, can be improved by a factor of 4 or 5, depending on the operating system or the kind of hardware that you're running on, especially on ARM. So today I will be working on many of those libraries, and if anyone wants to join, for all of them I've highlighted good first issues. So I realize that not everyone is writing themed assembly or using different languages within the same project at the same time, but if you want to try, there's like a lot of opportunity and I'm here to help. Me personally, I will probably be working on some CUDA kernels today. So our libraries, the open source ones, are not CUDA accelerated, but the internal ones have been CUDA accelerated since at least 2015. So if you want to work on similar stuff, large scale search and very efficient kernels, feel free to join me. Thank you.
Next we have Gavin from AGI. He's doing some super cool stuff with custom chips for transformers. So yeah.
Any other question or thought for?
Oh yeah, if there are any questions while you're connecting.
I have one question.
Sure. Yeah, Kyle.
How much room is there on like kernel optimization and search? Like it's like a very saturated place. So across these projects, like what do you think is like the main like angle if there's going to be another speed up?
So there's a lot of opportunity, especially like let's say there's opportunity in strings,
Sure.
but even in dense operations, auto-vectorization is not as great as people think, particularly like for more complex operations. So let's say if you're doing a dot product of single precision floating point numbers, you can be better than auto-vectorization, but by a small constant factor, let's say doubling the throughput. But once you implement more sophisticated kernels, let's say I had this long article last year where I compute the Jensen-Shannon divergence between 2 probability distributions. And this function can be used as a similarity measure for probability distributions. Unlike the callback library, it's symmetric, but it involves computing exponents or logarithms. I don't remember, I think logarithms. And in those operations, GCC struggles a lot, and like the compiler, any compiler you take struggles a lot. So manually written assembly ended up being 120 times faster than the assembly generated by the most recent compiler. And this is comparing assembly to C, not to Python. So the gaps can be pretty large.
Holy shit. Okay. Yeah, that's a great answer. Thanks.
Y'all know how I can get a presenter view working on these? How do I get the presenter view stuff working on the Macs?
Oh, and
The presenter mode?
How do I?
let me try. That's
You want like full screen?
He's in a very strange mode.
Yeah. Now I can't get my notes.
oh, you can't what?
Now I can't get my notes.
Your notes.
Yeah, that's fine.
Oh, I see. You want a different.
I think you have to basically
Yeah,
turn
you'll
off
have to
mirroring,
screen.
so it's
Yeah, turn off
two different
mirroring.
screens.
Yeah.
Yeah, I
And
think
slides
that's the
will pull
problem.
up one screen with the notes and one screen with the presenter side.
Yeah, in the top right, you can probably turn off the mirror. Yeah, maybe.
Yeah, that's what I was thinking.
Yeah. Food will be here in like 20-30 minutes, by the way, guys.
Yeah.
So. What is food? What, Jeremy? What is food again? Pizza?
So yeah, pizza.
Yeah, just change me right. Stop. There we go. Now we're cooking with gas. Now we should go to the slideshow. Now we should go to that view. So over there, there's no window here. So that window goes over there.
Also, is everyone on a Slack? All right, let me shoot out a Slack invite link right now in the particle for all of you.
Sorry, can you pick it back? Sorry, can I grab you back for a sec?
Jeremy.
Jeremy,
Yeah.
how do I get the displays up? I'm a Windows man, sorry.
Oh, okay. Oh, this is Ron's computer. Yeah. So you spotlight
No, this is
command,
not like
command space. Or, add Windows.
Is it down? Wait. Oh, it is too low. Yeah. All right. Wait, why would it let you move?
Looks like,
This is so weird.
there we go.
There we go.
Beautiful.
Oh, dude.
Okay. I don't think we're gonna get the full screen thing working, so we're just gonna go like this. Gavin, I'm one of the guys that etched. We're building very specialized chips just for transformers. But despite building chips, I'm not talking about that today. I'm going on a rant about flash attention and the way I think a lot of people do it wrong and how we can do it right. So how familiar are we with flash attention? Raise your hand if you think that you have a good understanding of how it works. Alright, we'll do a little bit of a refresher. So, what is self-attention? We are computing attention on three matrices that we're calculating, Q, K, and V. All we want to do is calculate Q times KT, divided by the square root of D model, take the softmax of that, and multiply it by V. Great. What does this look like in practice? Forget the math terminology, we want visuals. So the right way to think about this is that if we have a model with a context length of 5 previous tokens, there are going to be 5 Q vectors, 5 K vectors, 5 V vectors, and if the head dimension is 2, we'll have 2 numbers for each of those. And we don't have to keep them. That after we've computed the first 5 things, we can delete all of this stuff. All we have to retain are the Ks and the Vs. What happens when we want to do the next token? Well, token 6 comes in. We compute the Q, K, and V values. And what we're going to do is multiply Q times K to get a value here. We'll multiply Q5 times K1 to get our next attention score, Q5 times K2, Q5 times K3, and so on and so forth. Then, we have to go take the softmax. Softmax, to do that, we take in our vector of values, raise e to each of them, and divide by the sum. So e to all the values, and then average it out. But the key is we have to divide by the sum. So we'll take these 6 values, add them up, and then divide. And now we'll take these divided values and multiply all 6 of these by these 6. So this times that, this times that, this times that, and so on, to get the 2 new output scores, and we can go continue. With me so far? Multiply this times that for that element, this times that for that element. Unfortunately, there's a little bit of a problem here. Well, first, now we can go delete these scores. But on any kind of chip, we have different kinds of memory. We want to go keep those attention scores in the very fast GPU SRAM, or the very fast accelerator SRAM. But with the previous method, we have to go store all of these values. And that means that as the context length gets bigger and bigger and bigger, we have to go store more and more and more values in the GPU SRAM. And we can't do that. We can probably store only a dozen or so. So, how can we solve this? Well, all we have to do really is multiply Q times K to get this attention score. And we're going to multiply this times V, and then we'll add it to a running accumulator. So it should be easy. All we should have to have is just this running total and these three values at any point in time. Except, softmax ruins everything. Remember how earlier we had to go divide all these values by the sum? We can't do that division until we have all of these values. So without softmax, we have to wait for all these to be computed. We have to store and save them. Then we have to edit all of them by dividing by this constant, and only then can we multiply by the v to get our final output value. But there's a trick.
Could we compute it twice, maybe?
Good thought, but not quite. Remember that this is a linear operation, right? So by the distributive property, we can just do this here, or do this here. So again, to go push some visuals on this, we're taking softmax. Softmax involves dividing everything by this constant, but because this is just a linear operation, we can go pull this out of here and divide by the square root of all the sums at the end. So now all that we have to do is go and multiply this times this to get this attention score, multiply it by v, add it to our running total, do that for all the values, and we'll keep two running totals. The sum of all these and the sum of all these. But that takes constant space, no matter how big the sequence length is. And then all we gotta do at the end is divide by the sum of all the e to the x's, and we're good. And just like that, we have flash attention, right? No, there's this other problem. When we're doing this, we're computing e to the x for all these values. These values can be moderately big, like 10, 20, 50 range. And e to the 50 is in the quadrillions. So this number can become huge. And floating point errors are going to become very bad if we have huge number divided by another huge number. So we really want to find some way to get our e to the x values to be accurate for these inputs. But if you think back to an algebra class in the distributive property, we have another trick. If you take the softmax of all these vectors, bear with me on the math. I know it looks scary. It's not that bad, I promise. Softmax of all the vectors. So for any individual vector, it's just e to that value divided by the sum of all the e to that values. And for a fraction, we can multiply the numerator and denominator by the same value and not change the fraction. So for any number L, I can pull out of my butt. We can just multiply e to the L on the top, e to the L on the bottom, or e to the negative L on the top, and e to the negative L on the bottom. And then, because if we have orbitals of exponents, these are multiplied, so we can just add the exponents. So this equals e to the xi minus L minus the sum of all the e's to the x minus L. And this is true for any L we can possibly think of. It works if the number's 5, works if the number's negative a million. This is known as floating point errors. But mathematically, we're sound for any possible number right here. So, let's just go find the sum, find the largest value in all the x's. And that way, e to the x minus, e to the I minus our value L will be e to the I minus the biggest x. And we guarantee that e to the I minus L will always be negative. And this is a great property, because any value raised to a negative exponent is going to be between 0 and 1. So just like that, we've restricted all these values to be in the range of 0 to 1, which we can handle really well. They call this a safe softmax, because it doesn't run into these overflow errors. And it's a very clean, very nice trick. With one problem. To go do this, we need to know what the maximum value of all the attention scores is. So if we think back to our previous flash attention approach, we're going to multiply q times k to get this value, and then multiply that by v and add it to an accumulator, and then we go rescale later. Well, we can't do that because now with the safe softmax, we're subtracting this constant. We don't have the constant yet. But we have a third and final trick. What we're looking at here is the values of, hey, e to the something raised to e to the something minus or L times the v. What if we did this? We're going to guess what L is. We can guess anything. In practice, we just guess the max of all the values we currently see, but it can be anything. And then we get to this last value. This is what we have in our accumulator so far, and find that no, our guess was wrong. We guessed it was 5, and this new x is like 50, so that's not going to work. So let's update our guess to be L prime. And what we can do is multiply the current total by the difference between the two guesses. And then we can go and just add the regular thing. If we think through the distributive property, multiplying our guesses by L minus L prime is the same as multiplying every single value here by e to the L minus L prime. And if we just multiply these values, then we're adding the exponents, so the L's will cancel. And this will just equal e to the x minus L prime, the new value that we want. So the way that we can solve the problem of not knowing what the maximum is by guessing literally any value, and then when our guess is wrong, just correcting by multiplying by e to the x L minus L prime. And just like that, that's flash attention. This is the implementation that you see all over the web. It works just like this. But there's one final thing I want to go to. The thing that people...
Can I ask a question?
Please.
Did we already overflow though? Like we guessed L, our guess was bad, then we already overflow, then we multiply later on. Does that help?
Well, no, so the right way to think about it is that we want to have L be the smallest it can be, so that it's bigger than all the x's, right?
Right.
So what might happen is we could guess that it's 5. And then we could see an x later on that's much bigger than 5, like 50.
Right.
So now we have to go update our guess to be the bigger one.
Right.
So how do we avoid overflowing? Well, with this trick right here, we can pretend like our guess was correct all along by just multiplying by e to the L minus L prime. So in our case, where we guessed 5 and
Yeah, I
it became
guess-
50.
Yeah. But didn't like the thing on the left already overflowed, right? The sum.
No,
That's
no.
our guess. Probably
The thing that we're worried about is not the sum overflowing, it's the value of e to something big.
Okay, or maybe
So-
one of these individual ones overflowed.
So the right way to think about it is, hey, if we think originally that all these x's are going to be in the range of like 0 to 5, right? So we picked L to be 5. And that didn't overflow because 2 minus 5 is always negative. So this is in the 0 to 1 range, so we're good, right?
But what if our guess was wrong? X2 was 10.
All right, also this is the case where I'm showing an example where our guess was right for the first 3 and wrong for the 4th.
Okay.
And I'll get to the case where we're wrong multiple times in a second. But yes, what if we're wrong in our guess for x4? What if we thought the max was going to be 5 and x4 turned out to be 50 instead? Now we compute 50 minus 5, and that would be 45. E to the 45 is huge, so we would overflow as we say. And that's why we need this trick. Instead of doing this, we're going to take e to the x4 minus our new guess.
Oh, okay.
The new
We
guess is
updated
L
it.
prime.
Okay, gotcha.
The old guess is L.
Gotcha. Okay,
We
sorry.
take the difference,
Yeah.
e to the 5 minus 45, and multiply that through, and it's like we had the old guess all along.
Where's the overflow check happening?
This is a good question. I'll get to that in just a moment.
Sure.
But in practice, the way that this works is we go and look for we keep the total max of all the x's that we've seen so far. If the new value is bigger than the old maximum, then we overflow and then we do this. Otherwise, we keep the same approach. So, seeing that written out looks like this. We keep the running biggest one that we've seen. Every time we go compute this new di prime, this looks very scary, but it's not actually that bad. Because if this didn't change, then our value here is going to cancel out, and the d will stay the same. So then we just go take this new guess, and we divide it out by each element. And that's the last thing. Flash attention, as implemented by many people online, requires dividing by this new thing every time. floating point division is really, really expensive though. But it's better than going and reading from memory. So people do this and it works okay. But remember we said that the math works for any L. We can pull some number out of our butt, it'll be totally fine. So what we can do is just take this di prime and round it up. Find the nearest power of 2 that is bigger than this. And the cancellation will still work in the exact same way. And that way, if we're just dividing by 2 to the 26 or 2 to the 2, it becomes an easy addition. Dividing by a power of 2 is trivial. So, we do have to make sure that at the very end we have the truly correct value. We have to go do one floating point division at the very end of the operation. But this trick keeps the number of floating point divisions to be equal to 1 always, instead of 1 for each block. So, there's my spiel. I think I went way over, I apologize. But please stop doing floating point division every time you run flash tension for every block.
30-second pitch on like what Etched AI is doing.
Oh, yes.
Super cool.
Etched is building very specialized chips for just transformer inference. We are burning the architecture into the silicon, so you can only run transformer inference. In exchange, you get way, way higher throughputs, like 240,000, Llama 2, 70B, FP16 tokens per second. And if you like low-level problems, like working through the math and finding ways to go take floating point division out of the operators and save valuable silicon area, then come work with us.
Maybe time for one question. I guess we had questions during the. Oh, yeah.
Any chance you already profiled flash tension and found like what percentage of time spent doing the division? Or
It's not a huge percentage of the time. This is a small improvement
okay.
that shaves off like single-digit percents. It's not a huge problem, but it is one of those things that's totally unnecessary. So I'll shake my fist a little bit. And for building silicon, it's actually a huge problem because you have to have a floating point division unit on your chip, and a lot of them, if you do it the old naive way. So if you're building silicon, makes a huge difference in the amount of area your block takes up.
I guess maybe one more question.
Sure.
So, how applicable do you think your chip is for non-transformer based architectures, and how do you think about like maybe building chips without floating point units at all, just focusing on integer stuff?
I am generally a pessimist for integer quantization. I think that a low precision floating point is probably going to win out in the future. Also because the multiplier for int8 is more expensive than the multiplier for FP8. I don't think folks realize. So it's cheaper, it's more accurate. I like low precision floating point. As for alternative architectures, Etched is a bet. We can only run transformer inference, and nobody else in the industry is crazy enough to go wager on a single kind of model. But it is that bet on a single model that gives you the order of magnitude performance improvement. So if we are right, and there's a market for transformers in first half of next year, we will be the most performing chip on the market by an order of magnitude. And if that gets you excited, come work with us.
All right, awesome. Next we have Wasper talking about their super cool WebAssembly runtime stuff.
Go. Awesome. So I'm Sirius, I'm the founder of Wasmer. How many of you have used Docker or know what Docker is? Hopefully, like most of you. So we are the evolution of Docker. Docker, basically, like when you create containers for Docker, they are created for a specific chipset and normally a specific operating system. What we are doing is we are using WebAssembly, which is a technology that was created on the browser to be able to create containers that run anywhere, on the browser, on your phones, on your servers, basically like in any place. So yeah, basically like I created Wasmer around like 5 years ago. Rust shop. I'm not like much of a C++ expert, And yeah, we are trying to create this vision of universal containers. So more or less like the evolution of Docker. At the beginning, we started with abstracting on CPU instructions, which is basically like what WebAssembly is for. And one thing that we are trying to start researching on is not just for CPU compute, but also for GPU or tensors. And this is one of the things that we are investigating on. I might just do one or two simple examples just to see kind of like how Wasmer works and what Wasmer is. So this will go to the Wasmer, a little bit of a spam here. Hopefully you're all okay with that. So we got like programs that, in this case, for example, is Cause, like running fully on the browser. We have actually created a new container system that is much more optimized for O1 fetching. Basically, Docker has certain issues where, like, if you want to basically run a container, you need to sum all the layers to be able to use them. And in the case of the containers that we are creating, that's not necessary. And there are a lot of cool things that we can do. For example, running a Wikipedia search on an index that is actually like not hosted on your local system. And this is because we can do like fetching at O1 speed. So yeah, basically here we got like Cause running. Cool thing is this program is exactly the same one as you will install when you install Wasmer locally. Wasmer at the beginning, if you know what Node.js is, Node.js moves JavaScript to the server side. We are doing something very similar to WebAssembly. Basically, we have created kind of like a system that compiles these WebAssembly instructions into CPU instructions. There are like 3 different compilers that we use. One is LLVM, which probably most of you are familiar with. We have another one made in Rust called CraneLift, and we have another one which is handwritten by us, which is linear on compilation time, which is quite challenging to do. And that's called single pass. But the cool thing about Wasmer is that you can compile your programs or can be used literally anywhere. So even your Rust programs that are using Wasmer can be compiled to the browser. So I'm going to do a very quick example of something that is super cool. By the way, we have created one system called AGI layer. I'm not sure if you know what libc is. So we have created kind of like a libc for WebAssembly called WASIX. And the cool thing about that is we got programs such as Bash even running fully on the browser. And this is actually challenging because you need to save the stack, you need to do a lot of like shit to be able to run, but you can do like things like this. And it's actually not emulated, it's actually running fully, and you can do things like Wasmer, wait a second, run without say hello. Hopefully this will work. And yeah, basically this is fully Bash running. Here we go. So I can do actually run Bash inside of Bash. I can exit. I can whatever. So this at the beginning we are doing same as Docker, but being able to run anywhere. This is super cool for universal libraries, universal programs, and containers. But yeah, we are right now researching into going one step further. And this one step further is actually being able to run both Python natively, which by the way we also got it running, but also Clang natively. What's natively look through Wasmer? What's cool about that is that we can actually get full Python modules working fully on the browser, like basically without any kind of like extra step necessary, like NumPy and all that. Why? Because we can kind of use Clang to compile things locally. Either way, this Wasmer, there are like many cool things that we want to kind of like do. By the way, I'm from Spain. I'm moving back to Spain in 2 weeks. No, actually in 1 week now, and I'm actually on the process of moving. So I cannot stay here today for very long, but for 1 hour more or 1 hour and a half, I can stay here. Anything WebAssembly, I'm happy to help for like any team. And yeah, we are trying to do the next thing to have universal containers based as well on GPU instructions like Onyx and so on, and to have like containers that are basically fully runnable from your phones, browser, and so on. And the challenge here is how we can get models that are like super large. In a way that like without actually fetching the whole model, how we can compute on that model or inference on that model easily on the browser. So there are like many challenges to have here. And yeah, that's a little bit about me and Wasmer and so on.
Did Wasmer figure out a way to back up the 32-bit 4 GB limit in logic?
So right now there is the Wasm 64 proposal. Right now it's in phase 3, about phase 4. Phase 3 means like all browsers are implementing. Phase 4 is like when they have already implemented. As far as I know, MScripten supports like a 64-bit memory, but you need to enable a flag in Chrome to be able to use it. But this shall be usable pretty soon on the browsers. I give it less than a year to have a 64-bit memory. Why this is important is when you want to use models that are like larger than 4 gigabytes or any data that is larger than 4 gigabytes. Usually, like you cannot do that on the browser, but that shall be enabled pretty soon. The cool thing about that is normally you have like 64-bit programs that have like a memory space of 64-bit memory, but normally you do that as well for functions, which is usually not needed because you have usually programs or binaries that are less than 4 gigabytes. Cool thing is in WebAssembly you can use like small pointers for 32-bit pointers for like basically most of the function compute, but use 64-bit memory for data. And basically, like you can get even much faster performance on the browser or outside.
I think we'll probably have to move on.
Sure.
But yeah, definitely come find Sears after for more talks. I think next we have some people from the PyTorch team at Meta and NVIDIA Inference talking about what they work on and you guys are talking together, right?
Yeah, kind of, yeah.
You my laptop?
Honestly, it's fine. So, hi everyone. I'm Archie. You want to get intros?
The mic does not.
Oh,
Like it's on.
I'm Everett.
We can use it, but it's
Hi everybody, my name's Lake.
So before we begin, we're not official representatives of the team or anything, so we're gonna keep it intentionally brief. But if you're interested in what we're working on at like Meta and inside the PyTorch team, you're welcome to come chat with us after. So Everett and I work together on MTIA, which is the Meta Training and Inference Accelerator, which is our custom chip that has been it's designed to handle our internal ranking and recommendation workloads, and we maintain the whole software stack for it. So that's compilers, kernels. Firmware is not necessarily our team, but we still develop everything in-house at Meta. So we have a pretty big variety of things that we cover. It's a cool space to work in, certainly. And I personally work on the graph compiler side of things.
I work on the kernel side of things. The important thing to note here is MTIA is RISC-V based and partially open source. So there's a paper online if you search for MTIA.
The very first link.
Information about the first generation. The headline is 100 tops at a 25 watt TDP. More than that, I don't want to sort of get into publicly. But I think Mark has talked a little bit about his commitment to open source, and so I think it's an exciting team to work on.
You want to mention?
Sure. In my day job, I'm a product manager for inference software at NVIDIA. One of the projects that I'm interested in getting started here is bringing FP8 into the open source software ecosystem. Partially due to the lack of hardware, a lot of the popular inference software libraries out there don't support FP8, even though you get through the data, I see no degradation in accuracy, and half the bits means basically 2x performance, particularly for memory bandwidth bound use cases, which LLM inferencing often tends to be. And so this is kind of a software problem. It's a pretty easy one to solve and bring to the community in open source. And so that's something I'm excited to work on today.
Cool. Yeah, I think this begins our slow transition into lightning talks. Yeah, so I think there's a Jeremy blasted out a lightning talk spreadsheet. So go and sign up if you want to give a lightning talk. This can be about your idea, what you plan on working today, and feel free to give context of stuff you work on day to day to give more details on what you're trying to build. I think Dave is going to be talking next. He's first on the lightning talk list. So yeah, go sign up if you want to just briefly pitch your idea and help find a team. This is mainly a team finding metric, team finding method for the event. So yeah, Dave, do you want to? Oh, okay. All right. So all right, cool. Then next we have Jared Holbert.
So this is a really new idea. I literally had it last night in the car, but I'm kind of new to CUDA, to be honest. But near as I can tell, when you look at say NVProf or something like that, I can tell how much memory is owned, but I don't know whether it's actually used. And so in theory, what I'd like to do is use CUDA memAdvise and some other things and try to see whether we can actually see what memory's actually used and not just owned. So looking at kind of poking around at that, anyone wants to join or have some ideas or tell me I'm an idiot, please.
I guess next on the list is me. I'm definitely not like a systems level person. I come from more of like a NLP AI research kind of background, but it's definitely something I wanted to learn, and that's why I wanted to organize this event with Ash to get all these people in the room. So I'm trying I'm trying to just like dip my toes into CUDA in like some interesting novel way. I find that like working on like weird like theoretical CS type of projects often helps me like find my way around like a new area of research. So I want to work on like, so Wolfram Physics, they have these like hypergraph rewrite systems for like doing these physics simulations. So I'm trying to like see if I can write a CUDA kernel or set of kernels for doing these hypergraph rewrites for one specific interesting rule. So it'll be interesting from like a hypergraph representation perspective, like what's the best way to represent that on CUDA, because it's going to be very sparse. But then also in terms of like the rewrite rule, it's like doing the parallelized search across the entire graph structure for the left-hand side of the rule. I don't know how I'm going to do that. So I'm just basically going to be learning CUDA today. So yeah, if you are at a similar stage or also interested in Wolfram stuff, please reach out, because I might not be able to figure this out myself. Next we have Arjun, I think.
This is even less of a fleshed out idea. I had no idea I was coming to this until yesterday night when I decided sure. And so I had next to no idea what I was going to do. I did bring along a bunch of Raspberry Pis, so I'm probably going to try to do something bare metal on the Raspberry Pi. My idea was distributed inference for something like Gemma across Raspberry Pis, and bare metal to get the most out of the hardware and not have to deal with kernel overheads. More than happy to have anyone else with ideas of what to do with a shit ton of pies in my backpack come join me.
Like how many?
That's I can count. During the next talk, I will count.
I'm intrigued now.
Cool. Next we have Daniel.
Everyone. Also not that much of a systems person, but I think what's important to kind of help the business people understand the value of the systems work is measurement. And so I'm interested in spending maybe $10,000 today on trying to figure out the performance per dollar for managed vector search offerings on the market. So if you want to help me figure out how to quantify that, maybe write some load testing code, and warm up the ecosystem a little bit, then yeah, come find me.
We have Div is ready.
Sure.
Why don't just like connect my laptop to basic context? Sure. Sure. So I'll just try to make this short. Let's see. Cool. Cool. So yeah, so the idea I'm pitching is sort of like a personalized agent browser. So I'm working on this company called Meltdown, which is sort of like an AI agent that can do things for you. For example, like book price and so on. Just to show some context. So currently, like what we are doing is like this like browser extension that can go and like do things for you, say automate any sort of browsing tasks like booking flights, ordering food, sending LinkedIn connects, and then you can actually play with this. We are in a beta with 10,000 people right now. And what we think we're potentially doing is like, okay, like how can we take like new technologies like Wasm and web GPUs and all this like new innovations that's happening around like local models, and can we build this sort of like maybe like just like a new generation of browsers in a sense, where like everything can just run locally, but it could be automated. And then that'd be really interesting. So you can imagine you can have hundreds of different tabs, and all the tabs are like operating autonomously in the background, doing things for you instead of you doing things. And I think that'd be really cool. So here you can actually see this. So this whole slide is booked by the AI agent. Just going to the whole thing, and it's able to like choose the seats for me, and also like book the flights. So it's also able to like do payments for me. So you can imagine that there's just so many things you can do in the browser. Like 90% of the things that happen on the desktop happen in the browser. And so if you can build like some sort of like a future generation of the browsers, you can like sort of solve a lot of issues around like how do you, how work happens, how like a lot of things happen, how you interact with technology. And there's a lot of challenges here, like authorization, payments, trust, and then there's security and so many things. And I feel like that's just, it's a really big problem that if you can solve that right now. And you can actually do a lot of cool things with this kind of technology. So here we show like a flight demo. And then like the nice thing about agents is like they are sort of like the middleware. So if you can have an agent that I can interact with, I don't have to interact with the website or like a computer myself, I don't have to pick and type, because the agent can go do that for me. And you can do like a lot of fun stuff here. So here we actually had an agent go pass the online different driving test. So this was like a like zombie joke where the agent go and do the whole thing. This is like the live telephone exam. We actually did that in this house. So this actually went and did this. The DMV actually didn't know about it until we like started the exam.
My name in it.
Yeah. So there's a lot of fun stuff you can do. So that's sort of like the pitch where they sort of building the browser. We also have them. So if you're interested in sort of like working on technology on agents and the sort of like new generation of like how you interact with the digital world and the new like how you sort of reinvent how you are using your computers every day. Please feel free to reach out. Thank you.
I think we have Kyle next.
Is that me?
Yeah.
I'm Kyle. Can I go after?
Is there anyone else? Or Niels? Yes.
Yeah. I'm pretty sure I'm like on voting.
Yeah, we're at the bottom of the
Wow.
So last weekend, I built a thing that takes the Docker image and the Docker runtime, or any container runtimes, and puts them into a file so you can distribute containers as a single file and run them everywhere. But it only works on Linux. So I wanted to add macOS and Windows support. So the idea is to embed QEMU. So if anyone has experience with like using QEMU or like the Linux kernel, just embedding the Linux kernel, or experience with Zig, I'd love to talk.
Is Kyle still?
Yeah, I'm good. Okay, so there's like two things I want to hack on. One is a really, okay, I'll pitch the serious one first. Automated cost monitoring for infrastructure. So I want to basically do a graph traversal across all the different hardware that's running on a system and be able to figure out ways to cut costs on the machine. So, you know, typically when a human does this, you're running like HTOP or you're looking at system, and I want to be able to like have a couple, you know, metrics that matter, like how do I cut costs without impacting inference speed, and be able to like build kind of like an agentic browser, but on the lower level hardware side, because I think for context, I've worked on this for a few years of just helping teams optimize infra for ML, and a lot of it is just like you're a human RAG system that is, you're basically using ChatGPT and then you're querying like, how do I, like, if I change this thing, will it break the system? And so I think there's a way to like do that faster. So if anyone's interested in that or has the pain point of like cost, let me know. The other thing I'm trying to do, okay, this is like a really dumb side project, but like I like it, is, okay, I just broke it, but like basically I'm running an Ubuntu system, but I'm partially through modding it to look identical to Windows XP. So the I just broke everything, but you can see you can open the music folder. Oh, I just like broke everything. They're used, yeah. So I just bricked it. But basically, like, okay. What I want is when I turn on my computer, I want the GameCube opening to play like, and then I want Windows XP to load. But I want it to be running Ubuntu or like a Linux distro. If you know how to change like the boot settings to be able to do custom, like an animation, or if you know how to mod like sidebar stuff, it's like an icon set. I've got some of that working, but I think that's like a funny, I don't know, I think it's just funny. Like, so if you're familiar with like ricing, I really like hardcore ricing, so this is like a project there. So a couple things. Thanks.
You want to just write a grub theme or something for the prototype?
The what?
You want to be writing a grub theme for the prototype?
I guess, like, yeah, I'm not familiar with which like part to make the boot change, but yeah.
Okay, cool. I think, are there any other lightning talks that aren't on the spreadsheet? Cool. All right, so yeah, those are very interesting ideas. In terms of logistics, just a few things. Bathroom is over here. There's one over here. That's like most preferred bathroom if you're all the way downstairs and can't make it up or something like that, or like there's someone in here, there's also one bathroom at the very bottom. That is technically one of the housemates' bathrooms, but I think it's fine to be used for now. Otherwise, yeah, pizza is here, so we will, people are free to grab food right after this. We will get some drinks and snacks over in the next few hours as well. Food will be, dinner will be at 7-ish, and then we'll wrap up and do judging, or like demos at around 8. Otherwise, feel free to mingle, form teams, and get started, guys. Oh, real quick, Wi-Fi. The Wi-Fi is AGI house. The password is attention is all you need. Attention is all you need. Lowercase.
Actually one of the best things developers I know. Do you know X and Unpack? Do you know what X and Unpack is? It's like the CPU first runtime, the PyTorch and